I'll turn it over to you. Thank you, Colin.
Thank you, Dr. Allen. This came by welcome, everybody. I'm really looking forward to this. Unfortunately, the topic isn't very controversial, so we should be able to get through quite a few of the properties quite quickly because I'm sure nobody has any opinions about any of this. This came to us by Tony, was it? Who had gotten
Yeah.
a text?
Yeah, I just as a very short, so I actually own some Iconoclast cables. I'm very happy with them, and I know, just in terms of virtually, I know Bob and Galen. I met Galen at Axpona, and I think Bob reached out and asked if he thought our club would like a presentation by Galen. So I contacted you and Alan, and you guys took it from there.
Well, thank you so much, and I want to thank Alan in particular for shepherding this because his mother is sick and he's actually zooming in from his mother's house, and he may be in and out, but he's double checking on the Zoom connection to make sure that it's working. We've got 17 participants so far, so if everybody should be mute when you come in. There is a physical little hand that you can raise down at the bottom of the screen where it says reaction. And Galen has said that it's okay to ask questions as we go along. He'd rather have 10 slides with discussion than 20 slides without. So if you can either physically raise your hand on the screen so I could recognize you, or down on the bottom where it says reactions, there's a little hand that you can raise and it'll show up on the screen. And then thank you, Alan. And John, there you go. And then I can see who's next and kind of keep a list of who's got which questions next. So having said that, I'd like to give a warm welcome to Galen. I think this is going to be quite an interesting talk, and I've been looking forward to it quite some time. So Galen, if you're not muted, take it away.
Okay, no, I'm not muted. All right. Basically, the Iconoclast cables came about at Belden because we designed to strictly adhere to scientific norms. So in other words, we don't have terms that can't be measured, calculated, or tested. So I thought, well, what would happen if you tried to make a very high-end set of cables that push RL and C as far as we can in terms of making a theoretically perfect audio cable? Well, the guys at Belden said, well, knock yourself out, but you're going to find that it's pretty damn expensive and hard to do past where we are now. And they were correct. It was, but we did it. And the measurements and the like are all 100% valid. The argument, of course, is how good does a cable have to be for everybody to hear a difference? Well, you certainly can't hear a difference unless the cables exist to try. So we made them. And that's kind of where Iconoclast is that, Belden said, well, you can sell them on the electricals, but that's all we're going to support you on. We're not going to support you on anything that we can't verify in testing because we don't want to sell customers something that isn't absolutely true. So what I'm going to talk about today are the things that do make a difference in analog cables that can indeed be tested and are different from one cable design to another. All cable designers are faced with these problems, and basically you got to make a lot of compromises when you make an analog cable. I know a lot of people don't understand, well, what's there to compromise? Actually, there's quite a bit. Now, to understand audio cables, we need to go to the highest frequencies first, because this is going to explain a lot as we go down in frequency, and you're going to start to see how unusual the analog frequency band really is. This is a very simple, what's called a resonance method circuit. And the reason this is important is if you look at a coaxial cable, everybody here knows what coaxial cables are. You have 50 ohm cables, 75 ohm cables, 100 ohm Ethernet cables. Did you ever notice there is no impedance that's associated with a phase angle? It's just a number. It's 75. Why is it just a number? Well, something very strange happens when you design an RF cable. And that is if you take this oscillator frequency right here and you slowly increase the frequency until the phase across the resistor and the inductor are equal and opposite, they cancel each other out. So all you're left with is a resistive component of the vector sum. So the impedance ends up being a resistive value at RF. Now, this is only true at RF. As we go down in frequency, it gets all muckety mucked up, and we're going to go over that. All right. Now, if you look at the impedance of a classic cable, you'll see that this impedance is the square root of the inductance divided by the capacitance. All right. Now, what happens when we make our cable longer or shorter at RF? As long as we're at resonance and the R and the C are equal and opposite, if L goes up twice, C goes up twice. So the ratio between the two always stays the same, and the square root of the ratio ends up being the same thing. So a cable always is 75 ohms, regardless of how long or short it is, because it's a ratio with no vector or a phase magnitude associated with a vector. But remember, this is only true at radio frequencies. As you go down in frequency, we're going to start to see that that kind of fails. The other thing that's fun to look at, you'll notice on these two curves, we have an optimal spot right here for power handling, 30 ohms. We have an optimal spot for voltage attenuation. All right, minimum attenuation is 77 ohms, not 75, by the way, but 77. This isn't at 50 ohms either, because it's way out here. What happens here, again, is people had to make compromises even at RF back in the day when a lot of these standards were set up. If you try to design a 30 ohm cable, the dielectric ends up being pretty thin, and they didn't have the sophisticated dielectrics we do today. They had tar paper type dielectrics and things like that. And of course, when you try to put a lot of power through tar paper dielectrics, you end up with a lot of failures in the cable. So what they basically did, they increased the wall thickness, which increased the impedance until the dielectrics of the day worked extremely well and were very reliable. And they just kind of stuck to that standard, and we're still at 50 ohms today for generic type RF cabling. And that's kind of how that came about. Now, you'll notice that we also have 77 ohm cables for the maximal attenuation. I do not know to this day why on earth it's 75 ohms and not 77. It doesn't really make sense to me. So that one I don't know the answer to. Maybe someone out there does. Now, if you look at these as far as twin axe cables, you'll have to double that to say 150 ohms, twice 75. Likewise, down here in the 50 ohm cable, you'd have 100 ohms. But basically, anytime you're off of these two centers, you know that compromises were made even in the RF frequency region. And again, this is basically for optimal power handling or optimal attenuation. You can't do both. You have to pick one or the other. Now, here's where it gets kind of messy. And we start looking at impedance and we start to wonder what's going on. Well, here's our little friend, square root of L over C. We see him down here in the corner. That's what happens out at RF. Those two factors, all right, the square root of them are our impedance with no phase angle in theory. Now, we still we'll see in a little bit what actually really happens. As we go down in frequency, we start to see this dotted line occur. And that's called our transition region, where our impedance all of a sudden gets really complicated because a lot of factors. Remember your math class when the professor would say, he put some big messy equation on the board and you just sit there and go, oh, great, we're going to have to wade through all of that. I'll never get this right. Then all of a sudden he says, well, see, this term and this term, this is almost 0 and it's in the numerator. This is almost 1 and it's in the denominator. We can just throw those out. And by the end of the class, he goes from having 20 terms to 2. And you think, oh, thank God. So math is a wonderful thing when it makes our life easier by canceling itself out. But as we go down in frequency, nothing cancels out. As you notice, we went from a very simple equation to a complicated equation to still a relatively complicated equation. So we have 3 equations that try to fit this curve to what the impedance is really doing as we go down in frequency. Well, the first thing you ask is, well, why is the impedance even doing that? All right, why do we see this strange phenomena where the impedance goes abruptly higher as we go down in frequency? And notice this is 10,000 ohms at just 10 hertz. That's pretty high compared to where we were out here at 50 ohms or so. Now there's some...
And L doesn't matter at the low frequency, is that right?
Pardon me?
I didn't see an L term in the low frequency equation, so in that one, yeah.
Well, here's your low frequency equation right here, approximation. Okay, here's your transition region equation. And then here would be your high frequency equation. But there's going to be some inaccuracy here as they sort of go through these transition regions. So the best way to make sure these equations are giving you the right numbers, if you need them, is to actually do a test of the actual cable. Calculations are great on paper, but when push come to shove, Belden's measurements are all done on actual finished product. So we're not approximating anymore. All right. So, but these...
Galen?
Yeah.
Sorry to interrupt, Galen. I think the comment, though, was that at the lower frequencies, inductance does not seem to play a factor.
No, and we will see that in some further tests. Okay, so good question, and I will touch on that as we go, and we'll actually start to see the test results play that out. So that's correct. The cable looks primarily capacitive when you do what's called an open short test, and when you do an open-ended test, you're basically measuring the capacitive reactance of the cable, and the numbers will play that out. So the slides will answer your question in spades as we go. So again, good question. Now, that you brought up inductance, I'm glad you brought that up. We're going to see some interesting things occur at RF. If we look at a relatively simple cables down here, these are coaxial type cables or single pair cables. If you notice, the capacitance from 1 kilohertz all the way out to RF is basically dead flat. Doesn't change. As a matter of fact, MIL-C17D says you actually measure the capacitance at 1 kilohertz. Why? Because back in the day, and they had tube electronics, when you drive them real hard at RF, it decreased tube life. So they said, hey, there's no difference between 1K and 50 megahertz. So the standard is to measure capacitance at 1 kilohertz. Don't panic, because if you have a generally normal type circuit, you're going to see these numbers be identical. Now look at inductance, however. Notice all the curves start to dip down as we get to roughly 50 kilohertz to 100 kilohertz and higher. You notice the inductance drops, and it really does do that. Why is it doing that? Well, if we understand what inductance is doing at RF and at analog cables, when you bring two parallel plates closer and closer together, the inductance drops. So when the average current density inside the surface area of the conductor gets closer, the inductance is going to go down. And you say, well, we didn't move the wires in the cable. All we did was up the frequency. Well, when you up the frequency, you did technically move the wire, because you moved the current density inside the conductors from the cross section of the wire at DC to the outside surface at RF. When the current's on the outside surface of the conductor at RF, those two wires are theoretically closer together. Not theoretically, they absolutely are magnetically closer together. So now that the primary currents are closer together, you see the inductance drop. So when you do a lot of these measurements again, you have to actually measure the cables with a swept impedance to take all the stuff into account, especially if your impedance is super critical on specific circuits and across certain frequency ranges. So the inductance does vary with frequency, not a lot, but it does. So, and that's why, it's because of what's called the skin effect, pulls the current from the cross section of the wire to just the surface of the wire. That means the two surfaces of the wire are closer together in terms of where the current actually is, and that makes the inductance go down. Now, here's an example of a piece of 9269. This was a 93 ohm computer air core type cable. And we got the square root of L over C on the top, and it shows 92.7 ohms. Now, here's the other gotcha. You need to watch out for these units. This drove me nuts when I first started working at Belden. You almost want to go strangle people because they did not use units consistently. Sometimes a formula will be in picofarads per capacitance. Sometimes they'll be in farads, which means you need to put in all the significant zeros, e to the minus 12, e to the minus 8, because the square root of L over C is in farads, and the capacitance is in, or in the inductance is in henries. It's not in microhenries or picofarads. So you have to watch that when you use this equation. Now, if we use the MIL-C17D resonant method, which is a constant, which of course ends up being a single number after a whole bunch of jibber jabber is eliminated, it ends up being 101,670 divided by capacitance times the velocity. In this case, it's 13.5 picofarads, not farads, times 84, not 0.84, but 84. And that'll give you 89.6 ohms. So you see a slight difference in those two measurements, even though you're measuring the same cable. And that's because each equation is making slightly different approximations as to what the impedance really is. But they're both measuring the same cable. Now, if you measure an open short method, which is best for low frequency cables, which is what we're going to talk about more in this presentation. This gives us a better representation of what to expect on analog frequencies versus RF frequencies. Now, this works at RF as well, all right, but it's particularly useful for low frequency cables. So we're going to go away from the RF domain up here using these two equations, okay? And we're going to go down here to the ZO open short, where a lot of fun stuff can be seen in terms of how these cables actually behave.
So Galen, by open short, you mean it's not connected to anything at the other end when you're testing?
Yeah, you have an open, which measures your capacitive and your capacitive reactance, all right, components, and then you put them together with a short at the end of the same sample, and that'll measure your inductive reactance variables. Those two combined will give you your impedance. And that's why it's called open short. So one end, literally you take a 10-foot piece of cable and you leave the ends open, the two ends disconnected, then you short them together and then do a set of tests. And we'll see those actual numbers and what that does. And of course, what the phase and all that fun stuff actually does. So that's correct. Now here's an interesting slide. And here's what really can throw a wrench in the works. At RF, the velocity, the speed that your electromagnetic wave, not the electrons don't travel at the same speed as the electromagnetic wave. They travel much slower. But if you're looking at your electromagnetic wave, which is what VP actually is measuring, you're going to find that it will travel 1 divided by the square root of E of the dielectric constant. All right, that'll give you your dielectric as far as the calculation goes. When you measure it and you graph it, though, we start to see something strange happen. We start to see our velocity of propagation go from 80% in the RF region on, say, 9269, and it'll plummet to basically 10% or so at 1 kilohertz. And then you start to see this equation start to take into hand. VP is a square root of 2 omega R times C. This is an approximation for what's happening to the VP from a model standpoint that uses a certain range of RNC. Remember the equations in math class where you'd have two answers and you'd have negative apples? Well, you can't have negative apples and you can't have an equation that gives you a speed that's faster than the speed of light in a cable, right? So we know that if you make R or C low or high enough, you're going to get answers that aren't accurate. In other words, you're going to start to see where the cables tested electricals don't fit the equation. So don't look at this equation and think that it's going to work over any number of RNC values. It generally is designed and interpolated to work over capacitance ranges from maybe 10 to 20 puff and resistance ranges somewhere in the neighborhood of 22 gauge down to maybe 28 gauge in that ballpark. All right. So again, all these equations are approximations without a measurement. So they're good for doing lab work and to kind of see where you're roughly going to be and what's what, but you got to be careful with some of these equations. Now, if I look at 9515 and I actually look at the frequency and look at the velocity numbers and then just come over here and just look at, just pick it out and say at 20, kilohertz, we see it's roughly 40% velocity. We come over here and go to 20 kilohertz and basically, see if roughly our velocity numbers are matching that. And it does. It's showing it's roughly 0.41. So these are the measurements. These were the calculations, and this is the interpolated equation. Now, before we panic, when we say, you mean my audio frequency at 20 hertz is less than 20%? It's like, getting close to zero. It is. But here's our friend. Never, ever forget the speed of light is 3 times 10 e to the 8. That's damn fast. So what that basically is saying is, although there is a big speed differential between the frequencies, the ace in the hole for us in analog and on circuit boards and everything we make electronically that runs at analog is that some of this boo-boo that Mother Nature threw at us is somewhat mitigated because things move kind of quickly on relatively short lengths of cable so that the dispersion of our frequencies aren't nearly as bad as we might be led to believe. All right, so that'd be the argument for the people that say it doesn't make a difference.
So Galen, if I read this chart on the 24 gauge at 20 hertz, 0.01, that 20 hertz is going through the cable slower.
You better believe it.
Because it's such a big signal, because it's such a big wave.
Well, no, that you got your wavelength, and then you have the speed of that EM wave going down the wire, two different things. Okay. So the wavelength, it's going to be a time constant, 1 divided by the frequency, right? So you have that, but yeah, the velocity of that signal moving down the cable, you started at one end, how long does it take it to get to the other end? That's going to be determined by the dielectric constant at a specific frequency, because our dielectric constant is now dependent on frequency. All right. Now, some people will look at an RF cable and they'll actually do a bunch of tests across frequencies for super precision digital networks. And they'll say, hey, I need what they call a group velocity no greater than delta 1 or whatever. Basically, what they're saying is the dielectric constant at RF, I don't want that to change any. I want it to be 66% from 1 megahertz all the way out to 50. It can't vary from that. And they'll call that group delay. Well, analog audio has tons of what would be called group delay. The frequencies aren't all grouped together as they go down the cable. The longer the cable, the worse the grouping becomes. And you have to basically, recalibrate these things, especially on super long distances, which they did, by the way, with the telephone companies. They use inductive networks and things to kind of regroup the analog so that the voices would stay intelligible over long distances. So they had circuits that kind of brought everything back together and sort of regrouped it, mitigated some of the losses, and sent it on its way again. So a lot of this stuff was looked at by the Bell telephone labs back in the 20s and 30s even. Now, if you look at that equation and you manipulate R and C, you can actually create different curves of the velocity of propagation through analog frequency ranges. And if you look at analog, we're roughly right here. Here's our analog frequency range right in that little blue box. So there's a big change through the analog frequency range starting right in here. So to say that it's not occurring through analog is an understatement. It definitely is there. It can definitely be measured, and it's definitely real. And if you manipulate R and C in the cable, and here's omega. Omega is 2 pi f, frequency, in other words. So this is all frequency dependent. Now, this nice little pretty curve, hysteresis, you'll see Mother Nature likes to make these. You see them on transformer hysteresis curves and things like that. But the first thing we'll notice is as we approach 0 hertz, our velocity goes to 0. Why is that? Well, think about it for a second. What's the velocity of DC? It's always there. It's 0. So Mother Nature says, hey, if I'm going like a bat out of hell up at RF, but I go down to DC, the velocity has to go to 0 at DC, but it doesn't do it all at once. Mother Nature just kind of sneaks up on it, and we gradually drop down into the DC range to where we're seeing these really, really low velocity of propagation numbers. Now, we can sort of mitigate this curve and improve it here. We've improved the differential. We'd like to see all these frequencies go the same speed in an ideal analog cable, not ignoring RF right now. We want to make an analog cable, not RF. The problem with this is I can't get away from the fact that Mother Nature says DC is going to be 0. So the designer is forced with the RF characteristics of the cable to try to say, well, what can I do to make this curve less steep down here through the analog range? So I can kind of bend this down a little bit, which you see in these two different cables. Notice, however, up here, we start to see the velocity be the same. Why is that? Well, because I use Teflon as a dielectric, and it's 1 divided by square root of V at RF. So that says my dielectric constant is fundamentally going to end up converging on the same number as long as I don't change the dielectric. Now, the next thing you need to see is what is the speed on this particular cable? It's 50% at RF. Well, if I want to make this curve bend down and be even better, I would make it 30% and move this value down here. That means these two curves would further improve these two traces and make it more linear through analog. The problem is you're hard pressed to get this from 70 down to 50%, let alone down to 30%. All right. So again, the designer sort of has some trade-offs as far as what he can do to try to get this RF characteristic, which is based on the design of the dielectric in a cable. So it's not totally, in a coax cable, it definitely is 1 divided by square root of E. When you make a complicated analog cable, unfortunately, the dielectric constant is a superposition of many factors that give you your final RF dielectric, which you can test. And you'll see that it is, in this particular case, it's down into the 50% range. Here's some tests that were done. Gosh, these are so old, I couldn't even find the references as to who did them, but these are done in the 30s. And we see the same exact thing. We see, hey, impedance is groovy out at RF, but as soon as we get to the low frequencies, we shoot way up. So this stuff is not new. Then here's something interesting. If we look at the phase angle, and we'll talk about this with our open short test, notice the phase is 0 degrees at RF. We already talked about why that is, right? Because the square root of L and the C, the phase angles are equal and opposite. Our phase goes away. We have a pure resistor. If you look at your network card that's hooked up in your computer and you have a coax cable running to it or something like that, it actually terminates into a surface mount resistor. It doesn't terminate into inductance at a capacitor or some complicated circuit. It's just a simple, honest to God, 75 ohm resistor. And that's because at RF, that's what the cable looks like. So you want to terminate like into like. We all know that the old, put two transformers into the same impedance for the optimal signal transfer. So that's why we can do that, is we're 0. But notice what happens as we go down into the analog range. Now we're seeing the -40, -45 number. That's because it's capacitive in nature down at DC, and the inductance disappears, and we're left with mostly capacitance down here at DC. Does this really happen in real cables? Well, it actually does. Here's an open short test, okay, that we can look at. And if you notice, the impedance is the square root of the open times the short. Our phase angle is the open plus the short divided by 2. So if we measure our phase angles of the short and the open, we get an impedance value here with our open and short. That gives us 509 ohms at 20 hertz. Then if we look at the phase for the open and the short, and then we take the average of that to get the actual phase, we end up with -40 degrees of phase down at 20 hertz. So it is doing what the math and the theory says it should do. Now, if we go all the way up to the 2 megahertz range, look what happened. Notice what's going on here with the short. Now, notice on the open, our numbers are staying predominantly the same, okay? Now, on the short, you're starting to see the inductance become more and more and more like the capacitance, which means the phase goes from 40 degrees and it slowly goes down to almost 0 out here at 2 megahertz. See this number right here? Here's a little Easter egg in my presentation. I did these tests myself. What is this? That's a mistake. All right, I screwed the test up. So knowing how cables have to perform, I know that I made a mistake in this measurement because cable can't do that. All right.
Can I ask a question?
You sure can.
Okay, so you have 500 feet of cable there.
All
now,
right.
let's say 10 feet. I mean, these measurements will be definitely a lot lower and be probably less critical, correct?
No, your capacitance is still going to be -40 degrees and your phase is still going to go to 0. But on an analog cable, you really can't make a cable too long. That's the general rule of thumb. But if you do these measurements, it's always best to take cables and measure them at the same length. So to answer your question, yes, length does make a difference because of the wavelength of these cables. However, open short mitigates that better than any other test method. So if you're measuring cables at low frequencies, you really want to use the open short method, and you want to make sure that you're comparing like lengths because that'll improve the accuracy of the test. So does that answer your question?
Yeah, that's good. Thank you.
Okay. Now, here's the next crazy thing. We all talk about skin effect. Well, when we talk about skin effect in a roundabout way, we are, but we aren't. We're actually talking about what I call swept resistance. As you increase the frequency on a line of cables, and in this case, we stopped to trace it like 100 because that's where the meter I happen to be using is accurate down to. But as you increase the frequency, you'll see these two cables behave in this manner, and this cable acts decidedly different. And these definitely happen in the audio frequency range because, again, here's 20K right here. So there's a big difference through the audio frequency range. Now, what I was doing, as you can see, is I was trying to get it to be 0 as far as I could get it based on the design of the cable. So I wanted to basically make the resistive characteristics of the cable as close to 0 as I could get through the analog frequency range. This actually is the exact same numbers, all right, as the short measurements on the open short test. It's just 1/2 of the open short impedance. Now, a lot of cable designers or people that aren't cable designers didn't understand what they're doing because they didn't realize they only did 1/2 of my measurement for me. And if we look at this, guess where this came from? Look down here at the bottom. Who did this? Nelson Pass. He said, you know, I took a whole bunch of audio cables and I found out that all these different designs behave radically different than one another based on the design of the cable. What he didn't really realize is this is just the short part of the open short impedance test and why analog cables do all sound different depending on the way that they're designed. And these are quite measurable. This is not new. This is not a secret. It's not a conspiracy. Cables do this. So really what you're trying to do is you're trying to make numbers that look more like this and get away from numbers that look like this, okay, which is more of a common zip cord. Now, the other thing, now, is there any questions on this, by the way, as far as what's going on here? This is not skin effect. This is skin effect plus everything else. This is a hybrid test that encapsulates a whole bunch of crap, but it does it with one repeatable test for the open short. All right, so again, this is a collective of all the characteristics that affect the apparent AC resistance of a cable with swept frequency. That'll include, you know, super exotic things, you know, that a lot of people like to talk about that aren't really well understood with cables, at least not on an analog cable standpoint anyway. But it's all in there. It's kind of like spaghetti. So you get that in a single test. So again, this is not, quote, classic skin effect by itself.
I have a quick question, Galen, if you don't mind. This is all interesting in terms of measurements, but once you actually attach it to a speaker and an amplifier, that is adding a lot more variables in. For instance, I think you run electrostatic speakers. I think I read about somewhere.
Yeah, I have both.
Okay, so I guess you may cover this down the road here, is that what impact, if you've got electrostatic speakers that are very low impedance at high frequencies or dynamic speakers and so forth?
Well, and then you got planar magnetics that look mostly resistive.
Right. How does all that factor in to the cable design? Or do you end up having to have specific cable types for each type of speaker?
You really don't. If you make a cable ideally 0, it's basically trying to get out of the way of what the speaker and the amp is driving. That's the whole point of trying to make a high-end cable, is you're trying to figure out a way to make the cable look more like it's not there, and that'll benefit any kind of speaker. Amplifiers don't like to drive reactive loads. They're tested into resistive loads, and that's done on purpose so that we get consistent test results, but we don't really test amplifiers dynamically, primarily because we can't. Because we stick a cable in there, we put a speaker on the end, which is radically different. Now the amplifier is trying to drive that. The damping factor changes with respect to frequency. All those things start going on. So it's really hard to actually say that you're listening to a cable either. You're listening to how an amp behaves as far as its frequency response, driving a cable plus a speaker. If you have a cable that's a 75 ohm load, the cable is going to make the least amount of difference, literally. We have a cable or a speaker that's highly reactive, then the cable is going to make a big difference. As a matter of fact, it's going to make such a big difference that some amplifiers will blow up if you put certain cables on them, literally, if they're too high of a capacitance. We ran into that problem in the 70s and 80s where we had Litz wire speaker cables that had like 1,800 picofarads per foot of capacitance, and amplifiers would literally catch on fire when you put those leads on there. And the like. So yeah, you got to watch it. Amplifiers, feedback circuits, and the like are only effective across a certain reactive load. And like it or not, really good amplifiers are just a few steps away from being oscillators, because that's what an amplifier really is. It's an oscillator that's made not to oscillate. So any amplifier, if you put reactive poles on it that are big enough, will start to oscillate. And cables, of course, start to do that, and so do speakers. So they're doing exactly what amplifiers don't like. And that's why Nelson looked at this. He wanted to get an idea, what are these cables doing to me when I design an amplifier? I want to make a good amplifier that's relatively immune from problems that people may encounter out there in the field. Now, here's an interesting thing that's also talked about, that at first I'm going to talk about this from an RF time domain, but we're going to see some slides that show how it can affect us at analog as well. This is a Ethernet cable, and I did 401 data measurements just to prove it to myself, and I plotted them all. So here's the impedance, and here's the return loss. This is the amount of energy that's reflected off of a 100 ohm load. Well, this number right there with the least amount of reflected energy is pretty much, oh yeah, it's right at 100 ohms. Well, duh, you know, you have a 100 ohm cable, you put it on a 100 ohm load. Well, I come way over here. This is a 100 ohm test point right there too, but it's only got minus 25. How can that be? They're both 100 ohms. Because one is resistive primarily, vector, and the other one has a lot more reactance in it. Because even if you try to make a cable a resistor, you can't. You're always going to have a little bit of phase involved in these cables. It's not going to be perfectly 100 ohms resistive, even though the formula square root of L over C approximates that it will be more or less averaged at 100 ohms. But you can take a value that's as high as 110 and a value that's as low as 85, and they can both be minus 30 dB. Why? This is basically, these two values have the same amount of reactance as a 100 ohm value. So basically, they all have the amount of loss terminated into the same load. And this is something that can really baffle people. But it's, again, the nature of the fact that an impedance is a complex number. People like to say, no, it isn't. You just said it. Square root of L over C is just 75. There's no phase. Well, that's theory. This is reality. Reality says impedance definitely needs to be discussed as a complex vector, or else this trace could not happen. And these are measurements. This isn't calculated. This is what cable really does. Now, if we look at the spectral energy of our analog sources, this was done by Paul McGowan. He let me use this slide, courtesy of PS Audio. But look at the energy density down here in the low frequency range from 50 to say 200 hertz. You've got, you know, this is 1,000 watts peak right here. And then as you're playing music, going to the mid-range, it drops down to 15 watts. You go to the treble, we're down to 1 watt. Well, we just got through saying if you want an RF cable to transmit as much energy across a load as possible, we want the load and the cable's impedance to be identical, right? We're trying to transmit majority of our power down here, but what's our impedance of the speaker doing at analog frequency ranges? It's skyrocketing up because the velocity of propagation is dropping. When the velocity of propagation goes down, mathematically and measurement-wise, our impedance goes up. So it's fighting us. It's going the opposite direction we want it to go. We don't want it to go up. There's no such thing, guys, as an 8 ohm speaker cable. It's virtually impossible. You're seeing cable numbers in a 200 and higher range in reality. And that unfortunately goes opposite the fact that that's exactly where we're trying to transmit the most power, which of course means that's exactly where we're going to see the biggest impact on signal resonances and the like is in the low frequency range. So a lot of people, when they play with cables, one of the things they'll point out is, you know, this cable has better bass than this other cable for some reason. Well, a lot of it has to do with this property of our musical signal right here and what happens when you use different types of cable. Now, if we look at the impedance of a speaker, what do we see? We see exactly this. You know, we see the impedance is, this is even high. This is going up to 1,800 ohms or 18 ohms, but it's nowhere near, say, 200 or 300 ohms, which is a typical, you know, high quality speaker cable might be. So you see a really radical impedance trace, and the cable's trying to match this. So what frequency exactly are we matching? We aren't. You're trying to get the general impedance of the trace to be as low as possible, but to say that a cable designer is actually matching it to the speaker, I'll be one to tell you that I can't. All right, there may be somebody better than me, but you can't match to this. Analog cables will not behave in this fashion. They aren't resonant circuits like this. This is what a cable looks like that's really measured. Here's a typical cable. Now notice our phase out here is 0 out at RF. Notice our phase decreases down to the close to 0 range down here. As we go down in frequency, we go up. This is a regular zip cord right here, by the way, that goes up. This is 1313A, for instance, just a zip cord. It's just a good old 10-gauge zip cord. Goes up to roughly 500 ohms. This is a highly complex Iconoclast type woven speaker cable that's designed to pull this impedance down as much as I can. So to say this is matching at 8 ohm load, well, if you want to claim that, sure, go ahead. The idea is to just get it to match anything as best as you can by lowering the impedance at the low frequency ranges, which is drastically needed if you're trying to make an analog cable act as invisible as you possibly can. But this is not and never will be all right, a double humped saddle type portive speaker cable impedance curve. It's going to be kind of a gradual, nice, smooth thing. Mother Nature generally doesn't do anything suddenly, and you can see that in this curve. So yes, it's quite a bit better than just a standard zip cord. The swept resistance of this is also flat out to past 20K, whereas the zip cord does not. It increased exponentially as you got up into the higher frequencies, starting at about 7,000 hertz. It started really taking off. Both cables, however, as you notice, exhibit the same property at RF, and bingo, you're seeing the same characteristics up here. They all turn capacitive at the low frequencies, and they all turn close to zero phase, square root of L over C, phase angles cancel out at the high frequency. So nothing here should be exciting or new, really. All cables do this stuff, and cable designers have to struggle with this all the time when they try to make a better cable. Now, if we look at our swept open short impedance on our cables, again, these are just different cables. This is like a zip cord, and these are just various different designs of other cables. Now, here's something interesting. Notice this is roughly 600 ohms. How many people have heard of 600 ohm cables from the Bell telephone labs? You heard about that a lot, right? You'd always hear about these cables that are 600 ohms.
Yep.
If you're in that industry, you'll hear that. Why is that? Well, when they started making cables in the Bell telephone days, they had cables that were 600 ohms at roughly 1K. All right. Now, with modern dielectrics, I can get a 600 ohm cable down at, roughly 20. In other words, if this were 600 ohms at 1K, this right here would probably be 3,000 ohms or higher. All right. So back in the day, 600 ohms with the common dielectrics and the economies of scale and what they wanted to do back then, they centered it right at 1,000 hertz. So the concept of 600 ohm cable is legit, but you need to look at the frequency dependent characteristics of the cable to know, to make sense of that. All right. So again, these are all very frequency dependent. Okay. So that's kind of the crux of my discussion in terms of what cable designers have to do with cables. Does it matter? Someone was talking about, the inductance. Yeah, the inductance matters as you go down in frequency, and working with that, you can pull this impedance down. So you have a couple things going on. You can flatten the VP at the higher frequencies based on measurable concepts. You can also change the low frequency impedance magic into low frequencies, and you can do it at the same time if you had good designs. What does that do? It does provide a cable with better measured and calculated electricals beyond a shadow of a doubt. How much does that matter when you hook it up to an amplifier and a set of speakers? Hard to say, because again, all amplifiers are radically different in terms of how they behave with reactive loads. So you basically have to try before you buy and see what you hear and how it impacts the kind of stuff you have in your system. I've heard a pair of Magicos driven by a plate amp. What was it? The Devulet plate amp. The difference was absolutely astounding when we changed cables on that thing. And I almost thought that there was something wrong with the connectors on the cable we were comparing it to, because it sounded so much worse. I said, "Now this cable, something's not right here." But it was right. And then I've heard systems where we put the cables in and we've heard small differences. And my recommendation was buy to what your ear can't hear anymore and just stop. You're not proving anything to your friends by just spending more money. And some people, it just bugs them if they don't spend more, I guess. But my answer is we make cable from common zip cord all the way up to the high-end Iconoclast. So you're free to try and see what these measurements do. One thing you can be assured of is the electricals, as you go up the line, do get better and better and better. But to get those electricals, the cable becomes much more difficult to make and much more expensive. So is there any questions, really? I mean, but again, this is all cables see these physical phenomena. This is not isolated to cables I'm making. This is any cable with a dielectric. The designer has to kind of struggle with this. And when you change the relationship inside the cable, physicals equals electricals, you're going to change the VP at the high frequencies. You're going to change the swept impedance properties. You're going to change the low frequency impedance. All these things are going to move around on you. So the designer kind of has to decide. It's kind of like the joke with the butcher with his thumb on the scale. You sort of have to decide what you're going to weight, where, and why.
Can you go into the gauge of the cable versus the dielectric, and how you would try to bring that the impedance down?
Yeah,
a certain combination that you would do, large gauge, good air dielectric? Is there something you would categorize that as?
All right, there's your air dielectric, by the way. I got a bunch of different backrunds on here I can show you. So we got the twin there. We got the extruder right here, extruder head, extruding a dielectric. We have a woven polarity. We have the series 1 and 2, the difference in the polarities. We got a picture of the plant, stuff all over the place, typical plant. But yes, now your question was, what does a cable designer do to trick this? I'll show you the trick. And we'll back up to it. Okay, here's the trick. See where it says R and C?
Yeah.
What you need to do is realize as long as you're using insulated wire that's insulated one from the other, in other words, they're all insulated with the dielectric, that R is the loop resistance of a single wire. So in Iconoclast, just using my product, I have 24 or 48 wires in there. If I take one of those wires and measure its loop resistance, that's the R that goes in there. If I have one 1313A, which is one big fat 10 gauge, guess what that R is? The R of one big fat 10 gauge. So I take that 10 gauge up and I splice it up into a bunch of little wires. That increases R. Well, as this number gets bigger, this number gets smaller. Mm-hmm. So that's how you would try to pull this down. The other thing you could do is you could increase the capacitance some, which also pulls this trace down. So it's the multiplicand of these two together. But you don't want C to get real high. All right. The reason you don't want to get real high is everybody thinks, oh, it rolls off the high end. No, that's not true. It is a first order filter, but that's baloney. It rolls off the high end, like in the megahertz region. What happens is it starts to mess around with amplifier's damping factor because the cable's becoming more reactive. And the cable driving your reactive loads, damping factor, and other electricals do change. So you want to make the amp look like it's driving a resistive cable if you can. So you try to keep C reasonably low and do the bulk of your lifting by changing R. So in the Series 1 and Series 2 Iconoclast, I've gone from a 24 gauge to a 28 gauge, which makes a big difference in this R number, whereas C only changes slightly, all right, between the two designs, 45 to 75 picofarads per foot, but the resistance goes up substantially higher. So that's why it drops this curve so much more from the Series 1 down to the Series 2. All right, so those are some of the things you can do. Now, here's the problem, though. When you're going to increase R and C, C is highly dependent on the design of the cable to keep it low. It doesn't want to stay low by itself. Trust me, when you put 48 wires in a cable, the capacitance wants to do nothing but go straight up. And that's where it gets tricky, is on paper, I could just draw a line straight across here if I wanted to, but then you got to get a cable to cooperate with you and actually do that when you test it. And that's where it gets really tough. Is the electromagnetic design of all of those wires and the cable, and why the design of Iconoclast is so much more complex in terms of this really intricate braided construction that I've patented that allows me to not only drop the impedance at the low frequency range, but also tilt the VP linearity down as much as I can as well. That took a long time to figure out how to get that to happen. I could do one end or the other, but I couldn't get both to work. And that's what a truly good cable should do, is work on and chew on both ends and try to make them both as linear as you possibly can.
Right. Thank you. One other question. If you're going to design for an all-active system and you're going to have a bass amplifier, a mid-range amplifier, and a tweeter amplifier, would the wires be different in the design that you designed for just playing the tweeter, just playing the mid-range, or just playing the woofer? Would the wires be a different design, or would they all be the same?
Okay, the answer is in the graphs if you know how to read them. If you're talking about low frequency range, notice the VP converges, even though it's quite a bit different at this high frequency range. You'll notice that they almost splice right together from 100 hertz and below. What this means is, why would you use an expensive Series 2 speaker cable compared to the Series 1 for a bass amplifier? As a, for instance, if you're bi-wiring to a set of subwoofers, in this case, it'd be a bi-wire. All right, you're talking about active amplification. I'll get that in just a second. But this still gets the point across. Down here, I could use a cheaper and just as good a cable and save you a lot of money. Yes. Now, when you're talking about interconnects, we have a Series 1 and a Series 2 RCAs or XLRs. Same thing. The Series 1 uses 430 gauges, which you primarily see the benefit out here at the high frequencies. And the 25 gauge will be, say, down here. The same thing happens here. So if you're coming to me and saying, Galen, should I buy a Series 1 for my bass amplifier going to my amplified speakers? I say, no, use Series 1 for your bass because it's going to splice right in. The VP curves are going to naturally go right together. They'll cross right over as long as you're crossed over roughly from 300 hertz on down, which is the normal range for a woofer, 300 or less, give or take. And then I would say use your Series 2 to go to your mid and your tweeter, because this is where you start to see this improvement take place. If you're going to try to take advantage of any improvement that's really there and see if you can hear it, it would be Series 2, mid and tweeter, Series 1 on your woofer.
Great. That's a great answer. Thanks.
So, well, it's not an answer in some ways. It's just what the physics says it is. I don't like to take.
Okay, it's a good interpretation.
Yeah, it's an interpretation of the physics in terms of if you're going to try something, this is what it suggests that we would do and why. And it saves you money too down here. So it saves you some coin at the same time, which is nice. I have a paper on how to use Iconoclast in by-wire and double by-wire setups and the advantages of what it's actually doing and why in terms of what's I use, for instance, I use double by-wire. I use 2 Series 1s in parallel on the woofer and 2 Series 2s in parallel for the mid-tweeter, for instance. So that would in essence be a Series 3 if you want to call it that. And that was in the design parameters from the get-go, by the way, was to do Series 1 as one step in the right direction, Series 2 is another step, and then using them in parallel would be the third step. In other words, 2 cables in parallel for the woofer will drop your inductance to half, doubles your capacitance, but we're still talking about short cable lengths, 48 inches. So I generally recommend that when people do that, to use mono amps with no more than roughly 4-foot pieces of cable just to be safe. You can actually go quite a bit longer than that, but I generally recommend people, hey, if you have mono amps, plop them down there, 4-footers, you're good to go. Okay, so
I've got a couple of questions if I may.
Yeah.
So, just wondering if these things are measurable as you described here today, why don't we see these measurements when we buy especially expensive cable? Why can't this cable maker say, here's what our cables do, instead of this? And I see they also use a lot of sophisticated materials to, silver, this and that, things that are expensive. I can imagine building those things. It might be pretty expensive, so I'm paying for all that. But is there a benefit from a physics or sonics perspective? Should I expect them to behave in a certain way or whatever?
Well, they won't. Here's the problem is, if I put race car tires on my GTI in my garage, is it now a race car?
No.
No. If I put race car tires on my Porsche, is it now a race car? Yeah, because it was to begin with, right? So don't confuse materials with performance. If the fundamental design nature of the cable is not sound, in other words, RL and C aren't showing you good properties that you would like to see in a more linear cable, who cares whether it's got race car tires on it or not, right? So yeah, I can put, it's called sales and marketing. Belden won't allow us, nor will my level of honesty being a trained engineer allow me to sell things that I can't physically and honestly say are different. Now, for the audio crowd, and I'm an audiophile, do these differences make a difference when you actually use it in your system, which is another complicated question, because we don't hear the same way we test. In this particular case, as I made these cables better on my system, it was like, wow, these really make a damn difference in my system. I really like these cables. Well, I had too many people say, you can't keep this a secret. You got to let audiophiles buy this. And I said, well, first of all, it's not a secret per se, because I made it like this, just like what I showed you here this evening. Granted, the patents that do it and make those improvements are patented and difficult, but the fundamental physics I'm using are industry accepted since the 1900s, literally, or even before on a lot of this stuff. So materials are only beneficial in the right chassis, so to speak. I can design a cable with silver or any metal, and all I have to do is take into consideration the skin depth thickness compared to copper and the DCR and stuff, and I can make adjustments and the like. But if I don't see an appreciable difference in the VP or the attenuation of these other numbers, I have to question the validity and the cost benefit ratio of my customer base to do that. That's why we don't generally use solid silver and things like that on the speaker cables, because all the calculations show, yeah, it's going to be a lot more money, but I'm not going to see a big enough difference in the VP and the like. You're not going to see this kind of a change. In other words, going from a 25 gauge or 24 gauge down to a 28. You see a nice big jump here doing that, but I can't get you that big of a change going with silver. As a matter of fact, it's even harder with silver because the DCR is going the wrong way. I increased the resistance to improve the linearity of the cable. I didn't decrease it. And everybody talks about decreasing the resistance of the wire. Well, Galen just increased it by a factor of 10 or more. Guy must be an idiot, right? No, the physics said that's what you want to do. The physics also says your design wants to make the VP down in the RF range look really crappy. 50%, that's a horrible RF velocity. But for analog, it's what you want. I'd actually want it down here if I could get it down there with the good design that was repeatable and didn't screw up my low frequency impedance doing it, which it does, by the way. So again, this is a balancing act when you design these things. Now, your other part of the question was, why don't you see these measurements? You can do them on anybody's cable. So can they. Again, they can send their cables to Belden and I can measure them, and no cable will escape what I've shown you today. When you do an open short impedance set of properties here that we went over right here, those are all the real numbers, including my mistake, which is kind of humorous. And that's another nice thing, is if you understand the philosophies of what you're doing, you can also catch mistakes by kind of going through the numbers and saying, hey, here's my capacitance and here's my phase. This should be going towards 0. What the heck is that doing there? This belongs way up here somewhere. But nonetheless, all cables do this. There's no cable made that's passive that doesn't do the things I've described here today. So again, I didn't want this discussion really to be about Iconoclast. I just wanted to be educational in terms of what all cable does. And when you look at a cable and sort of understanding what some of these physical parameters are doing, you get a better appreciation for how maybe the designer was trying to get it to work for you if you like the cable, or if you want to look at cables you don't like. Doesn't really, matter to me one way or the other. But
right. Now, we talked about tonight about stuff that the characteristics of cables change with frequency, and all those other things change with frequency, right? And the amplifiers behavior, speaker behaviors change, right? All of that stuff. But when you talk about things like digital cables and say power cables, those things that's not the same thing, right? Those things are not changing for frequency, right? Power is 60 hertz. And digital cables is not a frequency thing. It's just digital information being transmitted. So
digital has a big problem with frequencies, and you're looking at it right here.
Okay.
You need to maintain what's called a attenuation to crosstalk ratio and the signal level in digital for it to work well with eye pattern tests and the like. So no, just remember, this is a 100 ohm cable here, right? That's digital. Digital's not affected by anything. It's just square root of L over C. There's no phase. It just, all you have to worry about is attenuation. That's not true, because this is a 100 ohm cable over here, and I got almost 25 dB or more of return loss, which isn't very good actually for digital frequencies. And this is an Ethernet cable. So Ethernet cables they got 11 pages of test documents that they're tested to by the EIA, TIA to make sure they work. So never for a second think digital is just digital. Now, a good digital signal with the right bit error rate of 10 to the -8 is just digital. Now, the other problem with digital is you can actually have cables that are too short and have too much energy hitting the receiver, reflecting off the other end and causing all kinds of problems. As a matter of fact, fiber optics is prone to having too much signal, and they put attenuators in there outside your house. You don't know it, but the guy who put your cable in says, okay, I want a certain amount of power going to the receiver so I know that I'm not overdriving it. And he'll put in loads in the fiber optic line to decrease its performance while you're inside your house arguing over a connector that has a difference between 0.01 and 0.02 dB of insertion loss, when the guy outside your home just put in a 10 dB stepper so you don't burn out your input on your piece of equipment. So it's rather humorous because one side doesn't know what the other side is doing. But again, this stuff is, when you really get into this, it's a lot more complicated than you might imagine. 35 years of doing this has taught me that, and I still don't know close to all there is to know.
cable. Can we touch on that? Should we be overly concerned about power cables?
Here's the thing with power cable, your ground plane is what determines your blackness of your background in your system. And we all kind of agree on that, the amount of hash noise that your electronic makes and shot noise just as it's sitting there running, right? When your ground plane differential starts to change, in other words, all points in your system aren't exactly lit, in theory, 0 ohms, you're going to get a ground current running from from high to low. That creates a current, that creates hum, that lifts your ground floor. So people say, what's the biggest benefit of using a big honking power cable? And I say, well, if you got really crappy grounds in your system and you tend to get a lot of hum and noise and things like that, you're basically reducing your ground plane differential by using heavier gauge power cords. Is that a direct impact on the sound per se? Well, it depends. If it's high enough, you can hear hum. If it's low enough, below audibility, then it no longer makes a difference. So it kind of depends on how good your grounds are in your system as to how big of a difference it makes. Now, as far as RF goes, we use EPDM dielectric on our audio cables. Why? Because it absorbs RF. EPDM is a horrible dielectric for radio frequency, so it naturally absorbs it and attenuates it so it doesn't get into your equipment. Or stuff coming out of your equipment doesn't get on the power cord and go out, and bother everything else, like if it's a microwave oven or something like that. But your power supplies and all of those things, though, they already have massively good RF shunts to ground built inside of them, or else they couldn't pass the FCC tests that are required. How do you know that? Did you notice your IEC socket on all your equipment is not connected? It's, you can put any cord you want on your equipment, right? With your IEC socket. Why can you do that? Because it's a worst case scenario. When you send it to UL for the FCC test, class A or B, they plug that sucker into the worst case power cord out there on the market, and they test it for egress out into the environment, how much crap comes out of that device. And if it doesn't pass the test, they say, no, you have to use a captive cord, and then they have to put specially tuned ferrite beads on that cord to capture the RF that's trying to leak out and absorb it and turn it into heat. But you can't take that cord off that piece of equipment. Now, if you design really good equipment, any cord on it, no matter what it is, will always pass the test. So they'll let you use an open IEC socket. What that tells you is your power cord isn't really doing a lot with the RF characteristics. It's doing more for the ground potential between two pieces of equipment when you plug it into the wall. And that's kind of my stance on that in terms of what I think our power cords are doing for you and what I think they aren't. All right. People ask me about the RF absorptive qualities all the time. And I say, you guys want really high absorptive qualities. I'm giving it to you, but I think the big advantage of these cords is just getting a good old-fashioned, decent, low ground plane between all your pieces of equipment when you plug it into all the various different outlets all over the place.
Oh, thank you.
Okay.
Alan, do you want to go next?
Sure. Thank you. Yeah, fascinating presentation. Aside from all the measurements, I'm curious, all other things being equal, what's the relative importance of cable length on affecting measurements and performance? I've heard that. In fact, I was talking to Roger Sanders once, and he obviously is a manufacturer and a seller of electrostatic speakers. He has his own white paper on optimal cables, and he actually sells I'm trying to think, it's not a Belden derivative. It's another manufacturer that he recommends for his speakers. But aside from that, aside from the manufacturer, what is the relative impact of cable length on all these parameters?
Well, it's going to directly affect the feedback nature of your amplifier. It's a big thing. The more reactive it is, the harder it is for your amplifier to drive it linearly. That's the big factor right there. The longer the cable, the worse it gets. There's no doubt about it. Now, some systems are designed as a system. Vandersteen has a really nice amplifier and set of speakers, the Model 7s. He has to sell those with a special cable because he's designed his amps to use zero negative feedback on purpose so that it has the absolute best transient response possible. But when you do that, the amplifier is closer to oscillating. So you can't just put any old length or type of speaker cable on it. you have to use a very specially designed cable to avoid that amp from oscillating, for instance. So only use the cable he recommends to be used on that amplifier, because he recognizes the amp driving the speaker, driving the cable, has to be used as a system. He knows what it is, though, because he makes the speaker, he makes the cable, and he makes the amp. So he can move things around to get, in his mind, a better advantage in the amplifier that he feels makes it sound better than trying to maybe fully optimize the speaker cable. So in his words, Galen, I can use a speaker cable that's theoretically worse than yours, but the performance gains I make in the amplifier offset that by a factor of X, Y, or Z when you listen. And that very well can be quite factually true. So there's more ways than one to skin a cat. I'm generically trying to adjust the market as a whole versus a specific instance, but all amplifiers driving longer cables will not perform as well. So now, as far as the tests go, yeah, the test will be indicative of those links. L and C will follow the links, so will C. Now, what won't change, though, is the VP characteristics or the open short impedance, because remember, it's a vector sum, so length doesn't count. But the total reactive load on your amplifier just keeps going up and up. And cables are, by nature, capacitive more than inductive, and that will bother some low impedance, zero feedback amps. Now, I use them on T+A M40s. Those are a zero feedback tube type design. And I use double bi-wire, series 1, series 2, no troubles at all with those amplifiers. So I'm not saying that all zero feedback amps are going to burst into flame when you put, XYZ cable on them. That's not true. Or become so nonlinear you can't listen to them. The differences are subtle, but they're there.
So, Galen, to follow up on Alan's question, real quick, Alan, I'm going to steal your thunder. If I had to choose between long speaker cables, let's say I put my amp, on the side and the speakers are over there on the other wall, and I have to, one option is to have a long interconnect between the preamp and the amp that sits between the speakers. Or the other is to put the amp over here with closer to the preamp and then have long speaker cables. I mean, which of those two is a better trade-off? Long interconnects to the amp or longer speaker cables to the speakers?
There's been some argument that says you should run your speaker cables longer of recent days, but if you look at what's most affected by reactance, it's an amplifier, not an I/O output driving an RCA or an XLR. The reason being is when you drive along RCA or XLR, the current in the cable is technically zero. You're putting it into a theoretical infinity load, right? 47 k ohms or higher. So you're looking at pure capacitance in that nature. And the designer of those op amps generally design them for up to 2,000 picofarads to be linear. So they know what the load is. That's the key right there, is the guys that makes the XLR op amps and RCAs, they know the load. When you use the speaker cable on an amp, they don't know what your load is. They don't know what the cable is technically doing, even remotely. They know most RCA or XLR is somewhere in the range of 10 to 30 puff. Speaker cables can be 10 to 2,000 picofarads per foot. And speakers, of course, are all over the map on impedance. So my general rule of thumb is make your speaker cables as short as you can and keep them close to your speakers for that very reason. So the toughest job of any cable is a speaker cable in your system, in my estimation. And that's where you notice the biggest difference when you change cables, by the way. So people say, what should I do first? I say, do the speaker cables first. That's where you're going to notice the biggest jump.
Excellent. Thank you.
Okay. Any other questions on a...
Yeah. So Galen, if you're laying the cable directly on the carpet, is the cable being affected by the skin effect laying on carpet?
No, only if you're rubbing it and you create a static charge on the cable, but very few people I know rub their speaker cables and stick them on the wall to get them out of the way. It works with balloons, but no, it's not going to affect the performance of the cable at all. Now, the biggest thing about cable risers is if you route cables along a wall or something and you're near power cables and stuff like that, your magnetic field decreases with the square of the distance. So to keep your cables, even balanced cables aren't perfectly balanced. It's always best to put the cables away from each other, i.e. your interconnect and your speaker cables. So I recommend people use cable risers just to take advantage of the fact that, well, a magnetic field is 4 times less when you double the distance, kind of a thing. So just keep them apart. And the longer you run them together, by the way, it basically gets worse and worse and worse to where you'll eventually potentially have a hum problem if you run an RCA right along a power cable going all the way around your room, for instance. So from that standpoint, keep them apart. Otherwise, you know, you can create a hell of a trip hazard with them. I did that in my system, by the way. So I ended up taking the risers out. I made some little risers. I called them cable jacks that worked pretty nice. We decided not to sell them, but they were basically just designed to keep cables apart so you didn't have hum issues. You'd run your power cables underneath them, and then you'd run your speaker cables and stuff on top. And that would give you that physical distance where people would have hum. And I generally only recommended it to people that did have noise problems. One guy fixed it with stacking books on top of one another that he'd read. So he had his library laid out all over his room to get rid of hum. And he just asked me, Galen, do you have something that's not as ugly as all my Kurt Vonnegut novels from high school stacked on top of one another all over my living room? And I said, yeah, just go buy some existing cable jacks that are, you know, the height that you think is appropriate and, you know, go for it. So that was my recommendation to him anyway.
So Galen, oh, no, go ahead, Colin. Go ahead, Colin.
Well, I've got a couple more questions, so go ahead and ask yours.
Well, mine was kind of leveraging off of yours. So, Galen, what if you don't have coincident, let's say, interconnects or speaker cables and power cables, and you just have like a long interconnect run? Is there any advantage to separating those?
Now you're saying, when you say coincident, are you talking about crossing them at 90 degrees?
Or even anywhere remotely near? Let's say all you've got is a pair of interconnects that have to go from point A to point B, and it's a pretty long run.
Well, you know my answer to that, right? They're on both sides of your head. Do you hear any hum?
Exactly. Well, right.
So if you don't, you're good to go. Everybody's going to be sensitive to background noise way different, you know, than others. I had a jam session over at my house, and I had a dehumidifier in the other room running, which makes kind of a low hum. Well, it drove, you know, Jennings from Absolute Sound. It drove him nuts because his room is dead quiet, right, when he does his stuff. Well, I'm more of a hobbyist listener. I guess I'm not quite that anal to where I go in the basement and I turn everything off and make sure the furnace doesn't come on and all of that. He does, so he can hear the minuteness of all his equipment. So, you know, you got that. So everybody's a little different in terms of what they consider their absolute noise threshold to enjoy their music. But if you don't hear it, you know, I mean, you're good to go. That's kind of how I see it.
Okay, so Galen, does the direction of the cable make a difference? I've had half the manufacturers tell me yes on, I think it was interconnects I was asking them about, and the other half say no.
There's a grain direction for sure when you draw the copper. And as you draw it faster, you create more grains. So we know that for a fact. And as you grow more grains, the DCR does increase slightly. Since they made TPC copper initially, they used that as a reference and called it 100%. And as they improved the characteristics of copper, they renamed it OFE and OFHC and ultra pure OCC, yada, yada, yada. But basically, the defining difference was the number of grains and the DCR. But AC, or our music, is an alternating current, right? The current goes one way and then it comes back the other way. How do you orient an AC cable to that? What half of the sine wave do you want to sound, in essence, better, so to speak? Now, some people claim if I set my speakers up so they all go out first versus all pull in first, it sounds better. But the problem there is the very first nanosecond of music, that advantage goes away. So it's really hard for me as an engineer to catch a grip on that and say there's anything measurable that I could sell you other than saying the grains in all Iconoclast do go the same direction because of the way I've made them. But I don't mark that directionality. I tell my customers, flip them in for N, and I give them the sequence to do it so that it's plus, minus, minus, plus, minus, minus, and plus, plus. And I'll say, go through all the possible orientations and leave it the direction that you think it sounds the best to you. You know, because again, I don't keep track of it on the plant floor other than I know the way the wire comes off our spools. All 48 wires, the grains are going in the same direction. So you can flip them around at will until you think that you've arrived at something that you enjoy. But I'm not going to charge extra money to make somebody at the plant because it gets very expensive at the plant level, making this cable to have all the reels and all the inventory systems track grain direction on these. So based on the fact that I couldn't show a measurable difference other than saying, yeah, there is a grain difference. Yeah, there is a DCR difference on the different wires that we sell, but those are factual and you can take it to a lab and test it and come up with the same answers. But I can't come up with an answer that would suggest why you would want to orient it on an AC signal one end versus the other. So that's where I am on that right now until something better than me comes along, I guess. I don't know all of it.
Okay, what about ceramic plugs then? I've always thought ceramic plugs, sounded better.
Well, you want something that's not magnetic, and ceramic's not magnetic. So there you go. Yeah, metal plugs or something that's magnetic you don't want. You want a eutectic brass or whatever, plastic, whatever suits your fancy, but definitely don't use something that's magnetic.
Okay, thanks. Any more questions? There's
I do.
John. Okay, John.
I got a question. Like, at what point, like on a certain run of feet, where does it really make a difference? I mean, is there like past a certain point where you can noticeably tell a difference? Let's say from 10 foot to 15 to 16, 17 feet. I mean, will you hear a difference from that far of a run on cable?
What I can tell you is our recommendation and what we've sold. We've sold speaker cables up to 30 feet long on the Series 1 with no troubles from the end user whatsoever. We've sold our interconnects up to 60 feet long on the BAV XLR, no trouble whatsoever. So that's speaking from experience, not necessarily a calculated mathematical answer based on what your op-amp driver is going to be tolerating. And all your op-amp drivers are not created equal, by the way. There can be some really bad ones out there that aren't balanced very well. And there can also be in my early days of hi-fi, I had a Yamaha CA1000. Does anybody know what that is? It's that old, Absolutely. Yeah, it's an old Class A 0.08 harmonic distortion, gobs of negative feedback back in the 1970s amp. But it sounded like it was just brighter than all get out on my speakers. And I never really could figure out, why is this thing so terrible sounding? Well, I ended up buying a phase linear 400. We all know what that is, right? And I ended up getting a Harman Kardon Citation preamp. We all know what that is. But the Harman Kardon Citation preamp, as you know, has a super unlimited wide bandwidth, right? It just went literally to RF. It had no damping to the frequency response at all. It didn't roll anything off. That thing would oscillate like you would not believe if you tried to drive any length of interconnect cables whatsoever on it, because it was just super unstable. So not all electronics were that great, back in the day. They also had amplifiers that would also get blazing hot just sitting there because they were amplifying RF and they were feeding back. You couldn't hear it, but the amplifier thought it was doing the good fight, amplifying the RF to all it was worth until they would eventually go poof. Those were also out there. So you just a lot of it's equipment dependent. That's what's so tough about this hobby, is some of it is a combination of things, that you hook up that makes a difference. I mean, this presentation is just trying to show you there are differences in cables that are measurable. I know a lot of people will try to show you what doesn't look different, but then you're seeing a lot of stuff on these measurements that I can do every day that definitely shows cables are indeed different. And that if you want a cable that does test more analog-like, flatter, more linear, there are indeed things a designer can do. The argument, of course, is where's the line in the sand in your equipment to where you can no longer hear that. And I tell people, hey, stop, when you can't hear it, right? By all means, it's not going to hurt us any. We sell all these cables from the lowliest to the most expensive. So we don't have an agenda. This was just sort of something that audiophiles said, hey, if Blue Jeans could do this and get these Belden cables to us, we'd really enjoy it, because we really do know how these cables are made and how they're actually different. For the first time, really, it's not a mystery. Like a lot of people say that I don't have any measurements with these cables I buy. How do I know which one's technically better? Well, in our case, you do. You can listen to them and you say, well, Galen, I know this cable's better, but I can't tell. Then I tell them and get the last cable you could and stop. So we're not here to put anybody out of business. We're just here to provide a service for audiophiles for the first time that we think is a fair fight in terms of evaluating these crazy, well, hard to make, better cables. When is it a benefit to you and when it isn't?
So, Galen, am I going to get more benefit from upgrading my 15 amp circuit to 20 amp, or should I just get a better power cord?
I don't think you're using the full 15 amps. Let me answer that question in a practical sense again. I have two M40s that are 550 watts and 8 ohms, over 1,000 watts, into 4. I have them on one 20 amp circuit that runs my entire system through a PS Audio P20 power conditioner, right? So I get a little bit of volt amp buffer there because of the big capacitor bank in that thing. But when I'm playing music and looking at my meters, I'm peaking at 10 watts at like 85 dB nominal. So in other words, I'm not even coming close to what those amps could do as far as how loud they'll play. Now I am enjoying how good everything sounds, definitely, but I'm not pushing it past where that quality of sound goes away because they're power starved in any way, shape, or form. So my answer is, how much average SPL are you seeing? If you're pushing peaks of 200 watts or more, I would probably recommend upping your circuit to 20 amps. Yeah. But until then, if you're listening like most speakers are 88 dB roughly efficiency, somewhere in there, 88, 89, most modern speakers, you push 10 watts into that and you're getting peaks of 95 dB, no sweat. So for the most of us, that's fine, 15 amps. The power cord is only going to improve your ground plane differential from point to point in your system, which gets your noise floor low. It's not really going to do anything to make that amp get more power, if you know what I'm saying. That small amount of DCR in your power cord is not, it's just not doing that. It's more your ground plane differential, and it's collective. Remember, the hum you hear is a superposition of all your ground plane differentials and all your equipment hooked up, and it creates a current eventually through all of that stuff and causes problems. Ethernet systems and digital, it causes a big problem too. TIA has a big, massive manual on how to build a Ethernet wiring closet, et cetera, so that your ground plane meets spec, so that you don't wind up in trouble, even in the RF domain. So there's very strict rules and regulations on how high your ground can be above ground when you do all the tests. So it does affect RF as well as analog, different reasons, but ground plane is definitely important.
Can I ask a question?
Okay, John, we're close to the end here, so I expect you to ask him a really tough question and sock it to him.
No, this is not. It's actually. I just want his opinion on a type of cable, if that's okay. There is a cable Canary makes. It's called a Star Quad cable. It's a microphone cable and you can use it for a long distance. How do you feel that works with speaker cables or internet cables or anything like that? I want to get your opinion on the Star Quad configuration.
Well, easy. The gauge size you're talking about is generally meant for mics, so it's too small of a gauge size to really be an effective speaker cable. What you want to use is a Star Quad type, and it's called 1310A. And Mogami also has a larger gauge Star Quad that's not oxygen-free, high conductivity copper. 1310A is. That will also be used as speaker cable. And that actually drops your low frequency impedance down from in the roughly 500 ohm range down into the low 300 ohm range. So it does improve your low frequency impedance. What that cable won't do, though, is address your VP linearity at the high frequencies because it's one big fat gauge size, basically, and the DCR is too low. The loop DCR is too low to effectively improve your VP linearity. So it does half of the tuning, if you know what I'm saying, between the low and high frequencies. But due to the cost of doing the higher frequencies, they kind of say, oop, can't go there, too expensive. So we do sell the 1310A. We also sell the Canary, okay?
The Canary 4S11 or whatever, I think that's 14 gauge. That's a large cable. If you combine them, that's a pretty large cable, right?
Well, you mentioned their mic cable. They make a mic cable that's 30 gauge. So
okay, no, how about the speaker cable then?
Yeah, the speaker cable, the 1310A is a little higher purity copper than the Canary 4S11. That's the difference. One is TPC and one is OFHC.
Oh, I see.
You can wire them both star quad, and they both will reduce the low frequency impedance from the high 550, 600 ohm range down into the 300 ohm range, which is really nice because then you try to come closer to what your average speaker impedance is with a passive cable. So I have a paper on that. It's out on our website. If you look at the by-wire speaker tech paper, it goes through all of that measurements and everything. So it's just no bullshit. Here's what it does when you use these in these configurations. And that's why it exists, by the way, is it's a stepping stone. 1313A or 10 gauge zip cord, it doesn't really improve the low end or the high end in any remarkable way other than trying to make a decent cable that's not too expensive. That's very passive to amplifiers because you can make it relatively low capacitance with just a common zip cord. So it's easy on amplifiers, but it doesn't really give you the most linear analog experience. Then you go to 1310A or 1310A or the 4S11. That improves your low frequency impedance. And then you go to the Iconoclast, and that will reduce your VP linearity to 2 different degrees, depending on the complexity of design that you're willing to pay for. So the Iconoclast does both ends, 1310A. Bogami does the base, and Zipcord basically, well, it's Zipcord. It doesn't really pretend to improve anything. It just is what it is. The improvement is the improvement is the dielectrics we have today versus what were available decades ago. So and a Zipcord, I can't say that's really true. That didn't improve anything. The dielectrics are vastly better than the old days. So a Zipcord is still much better than it used to be by a long shot.
Interesting.
So there are progressions to the madness here in terms of what we're doing. And again, this is all on design and measurement and everything. We sell on the design and measurement. You can take any of these cables, any outside independent lab and test them, and they'll get the same numbers I do because we use all industry standard tests. So, and that's how we sell it. And how we recommend it is buy up to scale until your car can't go any faster on the tires you're willing to pay good money for and stop, I guess. So we're more hobbyists. We're more hobbyists at this at Blue Jeans than we are a business is probably the best way to phrase it, to be honest with you. So we don't have sales and marketing. I guess if I'm sales and marketing, I guess this is it. This is what we do.
I listened to, in fact, I think I have them. Is it Claris had some Onyx cables, and they were woven speaker cables. Does weaving the cable make any difference?
Well, we do it, so heck yeah. Right? If you go, how's that? If that's not woven, I don't know what is. So yeah, this is one of the magics of trying to manage LNC to do what you want. This is what I've done to try to keep capacitance going severely high while also lowering inductance. All right. And we do that by, weaving them. And that is done, all right, on a special machine, okay, that puts those things together. So yeah, definitely. And there's a picture of the machine right there that weaves those together. That's called a Niehoff, made in Germany. That's a super expensive braider that we use to put these together. There's not too many of those hanging around. Belden has a couple. I think they have one now because they're so expensive to run. But we have that. So yeah. But does weaving matter? Heck yeah, it matters. Physicals equals electricals. That's a little idiom we were taught at Belden our first day in the door, is all these electromagnetic fields are totally determined by where they are. If you look at the wires in space and imagine that the dielectric's not there, the dielectric's just holding those wires in a particular position at best takes advantage of how those magnetic waves interact with one another. And then, of course, when you start throwing a dielectric in there, it adds reactance in the way of capacitance. The inductance is set by the spacing of the copper, has no impact by the dielectric whatsoever, by the way. So it's all your dielectric's all affecting your capacitive characteristics.
Is there a ideal material for well, you're probably going to point at your cables or connectors. Is there an ideal material then for shielding the wire?
It depends on the frequency. It's all frequency dependent again. When you say shield, you mean as in RF and that kind of shielding?
Yes, the cable covers.
Yeah.
And I guess
well, you mean the dielectric, the plastic, or the metal?
Well, I guess I was thinking of the outside.
Okay, the outside then. Well, the jacket you mean, or the outer shield?
The outer shield on the cable wire itself.
Okay.
Not the connector.
All right, I'm still trying to nail it down. Now, the outer jacket doesn't matter because it's over a shield, for instance, in an RCA or an XLR. So the outer plastic can't be seen by the inside of the cable. So you use what's best for practice there, but not electrical. In other words, flexibility, flame resistance, UV resistance, all that good stuff. But it can't be seen by the cable underneath the shield because the shield's doing what it's supposed to do. It's isolating the outside from the inside. Okay. Now, as far as the shield goes, the braids and the foils, those are all frequency dependent. I also have a couple of papers on all the measurements and everything that impact that. Start to get my drift, right? This is all done with real measurement. But it does show how the shields work at the various different frequency ranges, and there are big differences in how these shields do behave. At low frequencies, though, the magnetic fields don't see the copper and the aluminum and all of that. It goes right through there. So you have to use balance, like in an XLR. So you have to passively reject the inside or outside noise, or you have to use other means of getting rid of the noise, as in keeping them away from magnetic fields, because low frequency B fields go through copper and foil shields, no problem. So your shielded XLR is shielding it from RF so that the energy that's getting to the inside of the cable is lower in amplitude. So whatever residual unbalance is left in the XLR is very tiny. No XLR cable eliminates 100% of the noise, even though they're theoretically balanced. Most cables are balanced in the range of 1.5% to 3%. So in other words, there's about 3% of boo-boo left over after they're passively rejecting the noise at the op amp.
So if I was to do it yourselfer, which I am not, is there a material then that I might look at for shielding my own cables?
Well, you got to first determine, do you have a problem with RF? Because if you don't, you might make the problems far worse by trying to put shields on your cable, because that'll increase your capacitance exorbitantly unless you know that the inners are designed for the shield. So a shield will always make the electricals underneath it worse. Number one, that's like the second rule of thumb is physicals equals electricals, and shields are bad, 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 unless the noise coming in is worse than the degradation of electricals underneath the shield. So if you look at an unshielded Ethernet cable, I can always make one of those far better in performance than one with the shield on it. I lose 3 dB or more, sometimes up to 6 dB of near and crosstalk. I have worse attenuation. Everything I need to make my attenuation to crosstalk ratio better, a shield will make worse. Okay, just by the nature of the fact that it increases reactance inside the cable.
Oh, thank you.
So yeah.
Remember, shield bad.
Yeah, shields are tough. Shields are, there are examples though where shields definitely make the situation better if you have enough external interference to really take advantage of what it has to offer. But if you're in a normal environment where your terrestrial issues are none, zip, nada, don't use shielded cable. Basically, it's going to hurt more than it helps. Especially if you bend them, step on them, deform it, all that stuff will then slowly screw up your high frequency electricals.
There are some cables that are shielded with cotton. How do you like that? Does that sound crazy, or does that actually, because it's a good dielectric, they say?
Well, it's a good dielectric, but it's not a shield. That's the key.
And not a shield. I mean, it's covered with cotton. I shouldn't say shield.
As long as you can keep the dimensions super stable, which is hard to do with a textile weave because they're soft and pliable, at the lower frequencies, it doesn't matter as much as at RF. For RF, it's an unmitigated disaster. But as you go down in the frequency range, the dielectric becomes less of an issue. All right. So yeah, you could use cotton at the very low frequency ranges and certainly wouldn't want to use it at RF though. It's kind of why kind of a thing though. It's not quite as durable as some dielectrics that we have and the like, and more expensive to put on. And of course, once you measure once you measure the capacitance, I'm more interested in, okay, well, what's the inductance? What can you do with that? In other words, don't look at just C. You got to look at L at the same time. You want L and C to both be low. The problem is when you're trying to make C low, it automatically makes L try to go high. So you have to use more complex electromagnetic cancellation to keep L low, and a cotton weave is only going to address the capacitive nature of the cable. So just because it has cotton in it doesn't necessarily mean it's going to be an outstanding performer. It may have, anomalies with inductance or some other things. So just the material by itself doesn't tell me enough. I'm a design guy. Show me the whole car. Don't show me the bolt that holds the wheel on.
Okay, thanks.
Okay, anybody else? We're approaching over an hour and a half. If nobody else has any questions for Galen, I really want to thank you. It was a little over my head, but at least you answered my questions in a wonderful way. Thank you very much. After we sign out, we're going to cut off the recording here shortly. After we sign out, if anybody's new to the group and wants to ask any questions of anybody else or tell us about your system, we can still hang out for a little bit and talk. But Galen, I want to thank you once again for all of this, and it was very informative. Are any of these slides available from you or from Bob?
Yeah, I can make this whole entire presentation available through Bob and, through the Iconoclast website. We can have them added. As a matter of fact, we can also just go ahead and we'll add the Zoom presentation on it as well. So you can pick off the Zoom part of it and the slides if you want. You can go through it at home at your leisure.
Okay,
no
Bob
problem.
Sent us an email with contact information and an invitation to ask more questions from you. And I sent that email to everybody that's attending this meeting.
But yeah, all our stuff is totally open public domain. We don't hold any secrets as to what and why we do things. That's probably why we're a little unusual. And we're also, some people say, yeah, you're very confusing because you do this. So we get that too. Too much information, but.
Well, I found it really stimulating. So thank you once again for putting the time and effort into this. And as I said, actually, I think, have all the names gone? If there's anybody new that wants to hang out, talk about systems, please, you're welcome to. But I'm gonna stop the recording now. And Alan said that it'll be available probably in a couple days or a couple weeks. And he also talked about doing some editing or something like that on it. I haven't listened to the recordings, so I don't know what they do with it. But once again, thank you, Tony and Bob and Galen. It was very informative.